Hello, welcome to the third lecture this week. We're going to wrap up our discussion of feedback controllers. The previous lecture saw us follow a loop around and all of the transfer functions that are required to represent the measurement, the actuators, the control system, disturbances, and so on. So this is where we got to last time. We can see our control system and we can see how the signal comes around, and then the comparator creates the error signal. The error tells us that something needs to be done because we're not at our set point. That could either be due to a disturbance or it could be due to a change in the set point. And then we've got the mechanism now with the choice of controller, choice of control parameters to make the difference. So we're just going to take a look through some of the key features of this before Professor Costas in the next lecture will talk you through the detail of how to implement them. We saw that this was our overall transfer function for both the set point and the disturbance. We noticed that they were different, but also they're similar. So this is what we call the servo problem. This is where we've changed the set point and the system needs to respond to try and match the desired set point. And here's the regulatory problem, which is where there's been a disturbance to the process and the process controller needs to get it back to where it should be. So there are some similarities and differences here. We notice that the denominator of both of these transfer functions is the same, very useful, but the numerator is different. And we know that the denominator is what determines the stability of the system. We went through this in the previous lecture, lecture 4, that each of these roots of the denominator, we call them poles, will determine the stability. And if we can keep the poles to have negative real parts, then that means that they're going to be functions that decay. That means they're bounded and they won't prompt a response that disappears to infinity and causes an explosion. So the control problem from a stability point of view is the same for both the servo and the regulatory problem because they've got the same denominator. So that's convenient. We can design our controller to be stable for both of them, which is a good starting point. So the choice of controller affects both the servo and regulatory problems. Now, whilst they have the same characteristic function, the same denominator, you can design their stability criteria satisfactorily based on that, but they don't have the same dynamics, and that's because the numerators are different. So it's not that they're the same. Stability wise they have the same behavior, but they do have different dynamics behaviors. In particular, we see that the effect of the control transfer function GC is going to be different. So if we look back at the functions here we have a GC on the numerator and here we don't have a GC. So this is going to have quite different transient behavior than the regulatory problem. And we note that the effect of disturbances is not considered in the servo problem. So we check that. So if you look at the servo problem, the disturbance doesn't feature in this. There's no D in this term. And likewise, the set point isn't featuring in here in the regulatory problem. So the two parts can be considered independently when you design your controller. So before we get into the details of how you design the controller and tune the constants and all of that, we can look at it and just get a sense of what's going to make a good controller. What are the constraints on it? Do you want a big GC or a small GC? Do you want this to have a large or small magnitude? So let's take a look at the equation and just get a feel for what's going to happen to it. So of course one limit is that GC tends to 0. So this is meaning that the steady state gain of GC tends to 0. What will happen? Well, here we've got a GC in the numerator, so that whole term will tend to 0. Here we've got a GC 1 plus GC in the denominator, so that's going to tend to 1, and we're just going to have GD ds. What does that mean? Well, that means we have an open system. The set point isn't going to affect what happens, so it doesn't matter what we make our set point, there's no response to it. and any disturbance just gets fed straight into the output via the transfer function GD. So that's the open system. There's no control in that. It will do what it wants to do. So the other consideration is, what if GC gets big? So then we look at this. So if GC is on the top here, GC is on the bottom here, +1. So the bigger GC gets, the more that this function is going to tend towards 1, because the +1 become increasingly insignificant. So if that tends towards 1, what does that mean? Well, that means that ys will start to equal ysp. Sounds good. Here, if GC tends to infinity, then the bottom of this transfer function will get bigger and bigger, whilst the top stays the same, it's just dg. So this transfer function is going to get increasingly small, and in the limit will disappear. Now that looks like great news. It's the ideal case. It would leave our output ys is just simply equal to the set point. What more do we want? So you can see that the more powerful the controller, the higher its gain. There's an attraction to that. Theoretically, an infinite gain would be perfect. You'd get the output as equal to the set point very quickly. Why is real life not like that? Well, this is based on a model of the system, and our model isn't perfect. We know that. We make assumptions about the transfer functions of the process. We approximate them as delay and plus first order response when that's not actually exactly what's happening. And so that means that if your process doesn't actually quite match your theory, and you've got a whopping great gain on your controller, then it's going to behave very dramatically when there's any small deviation from the ideal theoretical behavior. So here are some notes on that. You'd say that the system becomes very aggressive and sensitive to system changes. So that means that it just doesn't work very well. If the system changes a little bit, you have very large and perhaps unpredictable, undesired outcomes in your control and your output. And compliance is with the set point changes is not the only control objective. So also you want the transient behavior to be good. So that's other considerations apart from your control consideration. Your process has to satisfy other criteria as well. So you can see that there's the attraction of a large gain. So often you might want to be maximizing it as much as you can, but you'll find you get to a point where the system becomes hard to manage because it just doesn't behave quite the way we theorized, and then it would do odd stuff. Okay, that concludes the comments on the feedback controller. You've got a sense of what it's about, and you've seen the way in which we can compile it by putting the transfer functions in the block diagram sequence, and that's a neat way of building up a picture of the equations that will determine the behavior. Professor Costas will take over next week, and he's going to go delve into the detail of how to design these feedback control systems and look at other control systems too. I'll be back in week 10, so I will see you before then in problem sessions and drop-in sessions, and enjoy the course. Thank you.